based on what you think. For this question, all right. Let's start with the one I think which is the easiest one, which is you've probably seen before. X1 squared plus x2 squared equals 1 looks like a circle. So most people got that one right. This one is Pythagoras, right? A squared plus b squared equals c squared. And that's saying that if you want to get the hypotenuse of a triangle, you do the sum of the squares. So if x1 squared plus x2 squared is always equal to 1, then the hypotenuse is always 1. So that's exactly a circle. And of course, you can see that one in Desmos quite easily. So Desmos doesn't have x1 and x2, it just has x and y. So you do x squared plus y squared equals 1, and Desmos knows, hey, that means a circle. Okay, so that's great. So it's all the points in the xy plane where if you square the x coordinate and you square the y coordinate, add them together, you get 1. All right, that one is good. That one is the most familiar one. All the other ones are a little bit exotic. So let's look at some other ones. I think this one, if you logic out, if you just think logically about the maximum of absolute value of x1 and x2, you will eventually figure it out. So let's see what do people say for this one. Some people said rounded square, some people said square, and some people said star. I will tell you, it's either one of rounded square or square. So that's a hint for that one. Let's look at what do people say for the other ones. What about this one? This one is all over the place, so people don't know what this one looks like. I think save this one for last. Okay, what about this one? Absolute value of x1 plus absolute value of x2 equals 1. Lots of people said it's a diamond, and that is correct. So those people were probably watching the videos. So very good for you guys if you saw the video and you know it's a diamond. So the absolute value of x1 plus the absolute value of x2, or in Desmos you have to put it in with x and y, you get this nice diamond that looks like that. And of course this is really related to the lasso, which is why we're doing it today. So very good for those of you who got that. I will say you can really figure out what it is by doing cases, right? So the absolute value of x is either plus x or minus x. So there's sort of 4 lines that come together to give this thing. Plus minus x, plus minus y, you add them together, you get 1. There's 4 ways you can do it, you get these 4 lines. And of course, as soon as you're outside, if one of them is bigger than 1, then of course the sum will be bigger than 1. So it has to live sort of in there. So that's absolute value of x squared plus y squared. And those are the 2 main ones we're going to do. But it is interesting to see these other ones because what we're doing is quite general, and all these other ones are other examples in other universes, other versions of the lasso, and things like that. So some people here said star. So what are the ones that are still under contention? This one, and this one. So I'll give you guys a second to revote. You can talk to your neighbors. You can show them your Desmos program. Let's try to figure out these last 3. So you guys got the 2 most important ones right, but the other ones are fun too. So we'll do that. Okay, so I'll copy this over, and then we can we'll take another minute, and then we'll take it up. Okay.
Sorry, not a call. Yeah, that's I don't think that it's a like a square, yeah. I'm trying to see. Well, the last square makes sense. I think it's like a
Like you can't go anywhere outside of the points.
everything inside.
Yeah, you can't go
It's
anywhere
true.
that's outside of the line.
Yeah, it is on the boundary.
It is by as a square.
But it's not. It's
So
the boundary.
here, this
What
one
stays in
is here.
on
Well, okay, so I'd say it has to be a square because if x1 is equal to 1, then you have the top line. If x2 is equal to 1,
Yeah,
the top line negative.
we agree, yes.
Yeah.
I think that's
That's
just
great.
I'll do it just clear
I'd say.
I can know these are correct.
This one is star, yeah, it's this one is diamond, this one is circle. This one, you know, it seems to me it should be some sort of oval.
Well, there's no
Yeah,
square.
It's shape of square.
No, because
This is a little.
Yeah, like an actual square, not a diamond. Yeah.
So my son knows oval, and he wouldn't say oval to these, so that's why there's no oval on the list. Like,
How old is the son?
he just turned 3.
Mm-hmm.
Yeah. Okay, yeah. So yeah, which one did you think was oval?
yeah, no, I'm sorry.
I mean, you could like you could an oval again, like a rounded square,
Yeah,
isn't
yeah,
a
yeah.
real thing, right? Like it's just like a made up.
Yeah, I made a mistake.
So the one that's a rounded square, you could equally well call it an oval, and like there's nothing wrong with that. But I didn't put it on the list. If you want.
I mean, if you think of it like this one is a diamond, right?
Yeah,
You make a square, that's a circle, and then you give more exponentials, it like grows fatter.
Yeah.
In a sense.
But I wonder why we cannot draw this one.
The last one.
Yeah.
No, but
And this one.
Probably just the notation.
That's not right. You're not adding them together.
Oh, yeah. Right.
It's
Yeah.
what's that?
Yeah,
Because you
Shall
should
I start?
Yeah, that's what my son thinks that's a star. Yeah. Okay.
One by two.
Okay, if they've got function max, it should work.
You need to be able to map from one coordinate to another one so that you can have a point. I think.
Yeah, this doesn't,
And
this doesn't.
it's not a function.
Yeah.
Okay.
What are you saying
That
Well,
last one?
It's a square. I mean, it's literally can't go outside the line.
Yeah.
Okay, so it's been 3 minutes. Maybe I'll try to stop at 4 minutes. So put in your updated answer. I think most people are starting to get them. And we'll fill it in on Desmos. And I think some people are starting to see the pattern. Like all of these things are actually very closely related. It's not just like they're all different. They're all kind of the same thing, but slightly tweaked in important ways.
So the trick is to know that there's no x1, x2 on Desmos.
Yeah, so Desmos has a bunch of idiosyncratic things, and one of them is that the x-axis is always x and the y-axis is always y, and there's no way to relabel it. And it's actually there's another one that you should know. If you do t, so if you do like 2 times t plus 1 comma t, it'll automatically make t go between 0 and 1. So t also means something special, and then you get like a little line like that. So you got to be careful in Desmos. Yeah, it's like an art. Okay, so 10 seconds left. I'm gonna display the answers. Get your guesses in, and we'll take it up. All right, let's see. What did people say? 6 out of 6 people said the first one is a star. That is correct. So if you do the square root, so I want to do the square root. I made this great thing. I made x to the power p. And if p is a half, that's the square root. Something to the power of half is the square root. So I can do this one by doing 0.5, and it looks like this green star. So this is 0.5 is a star. So that's very good. This one we already did. This is a diamond. This one is the circle. Okay, what about x1 to the 6, x2 to the 6? Lots of people said rounded square, which is exactly right, and that is exactly the case. P equals 6. So remember, if we do 1, we get the diamond. If we do 2, we get the circle. Once you start doing numbers that are bigger than 2, you sort of bow out the circle. So when we go all the way up to 6, there's 6. And it looks like a nice rounded square. So when you like buy like a nice table at IKEA, sometimes that's what they look like. Okay, that's 6. What about the last one? I guess by process of elimination, it's a square. So the thing about squares and diamonds is they're actually the same, just rotated, which, that also confuses my son, because if you rotate it, it suddenly changes what shape it is. But this one I would say is a square. Is there a way I can make the green shape look like the maximum of absolute value of x and absolute value of y, or do I need to make a whole new equation? What do you guys think? And there was a hint. You saw what happened when I went from 2 to 6. It was starting to go like that. What if I just keep going? Like you keep going, and you keep going further and further. Okay, I went up to 10, and now it's like a really rounded square. What if we go up to 100? All right, that's looking pretty good. So the maximum of the absolute value of x and the absolute value of y equals 1. That is a square, and you can sort of simulate it by doing x to the power 100 plus y to the power 100. And all of these things are called p norms. P norms. And this is why I wanted to show you guys this in case you've never seen this before. And the p norm, it's something you do to a vector. So somebody gives you a vector, and in this case it's a vector with two components, x1, x2. In general, you can be given a vector with many components, but we're just doing it with two components because we have a two-dimensional screen here. And the vector, right, points in a certain direction. The norm is a number. So you do the norm of it, you get a number. And that number is supposed to be like the length, the quote, length of the vector. And this is the interesting thing, is that there's not just one definition of length. So the length you are used to is the L2 one, that's the circle. So the most common one is the L2 norm. You do the L2 norm. This is by definition the square root of x1 squared plus x2 squared. This is the ordinary length, but it's also called the L2 norm. And you denote it with a little 2. So you say norm subscript 2. If you don't write anything, usually this is what people mean. But this is the exciting thing, is that there are many, many possibilities. And in fact, I just showed you an infinite collection of them, because for any value of p, you can make the p norm. So let me write the p norm. The p norm of the vector. This, you do x1 to the power p plus x2 to the power p, and you take the whole thing to the power of 1 over p. So it's some kind of combination of how big x1 and how big x2 is, where you take them to the power p and you add them together. And if you take p goes to infinity, you get what is called the infinity norm. Infinity. And this one is the maximum of x1 and x2 in absolute value. Okay, I will say there is one small problem when you have negative numbers, right? So if you have negative numbers to the power p, things can go screwy. So usually people take the absolute value first. Let's put that there. And of course it doesn't matter in the ordinary norm, because when you square a number, it's already positive. So these are called p norms. There are other types of norms. So there are many, many other norms that are more complicated. So if you took a good linear algebra class and maybe did some norms, you can do norms of matrices as well. Anything that lives in a vector space that you can add together, there's a notion of norm, and it has to satisfy certain constraints to be a norm. So it's not like an oval or a rounded square where it's just like made up. A norm has a really specific definition. It has like properties it has to satisfy. And actually, the one that I showed you, one of these things is not a norm. All of them in the example were norms, except for one of them. Looks like a norm. It kind of tells you the length, but it doesn't satisfy one of the inequalities that it's supposed to satisfy. Does anyone want to take a guess at which one is not a norm? One of them looks a little bit more screwy than the other ones. So let me go back to mathematize. So our options were p equals a half, p equals 1, p equals 2, p equals 6, or p equals infinity. One of those is not a norm. Which one's the screwy one, the odd one out?
The circle?
The circle is the most boring one. That's like that one is definitely a norm. The star, so that's p equals a half. So it turns out this one is not. This p equals a half is not a norm, and it has something to do with the triangle inequality. So all of the other ones obey the triangle inequality, but the star one doesn't. And it not obeying the triangle inequality, you can see it visually that this shape is not convex. So a convex shape means it has no cutting end bits. And mathematically speaking, between any 2 points, you can draw a straight line. So if I'm in the blue diamond, and I pick 2 points in the blue diamond, and I connect them with a line, that line is also in the blue diamond. But that is not true for the green star, because if you take 2 points that are in the sort of corners over here, the line between them pokes outside of the star. And that makes the star is not a true norm. So some people call it a pseudo norm. It kind of behaves like a norm, but not quite. Why am I telling you all this stuff about norms? So norms are great. You can take a whole course basically on norms, in functional analysis or something like that. And for us, they are a perfectly good way to regularize, that's the long word, our estimators. So we saw already ridge regression is, ridge regression was this equation. You take the mean squared error, that depends on beta, and then you add on some constant, and we said beta 1 squared plus beta 2 squared. That was actually the L2 norm of the vector beta. So here beta is a vector, and we were doing the L2 norm. So this is, and we minimized over beta. This is ridge regression. And this is the L2 norm. So that's why I think a better name for ridge regression is actually L2 regularization. This term is called the regularization term because it kind of tames this term. Like this term might be a little wild, and you add this on and it behaves a little more mildly. It makes it more regular. And we saw that last time with, you might have a very long ellipse, like some kind of screwy ellipse, and then you add on this term and it makes it a more round, more nice. That's ridge, and today we're doing the lasso, which is the exact same thing as the ridge regression, but instead of adding on the L2 norm, you add on the L1 norm. So you do the 1 norm. And the 1 norm is exactly in this case p equals 1. It's the sum of the absolute values. All right. Let's see, L1. So a better name for the lasso, like I don't know who is naming all these things in this class, but they're like crazy things, right? The lasso, like who? That you can't call it that. That's illegal. The lasso really is just L1 regularization, and you can do this for any p, right? You can add on any p. You can add on any other type of norm. If you kind of know something, you know some properties of the thing you're trying to minimize, you can put on any norm you want, and you can come up with something. And we're going to see exactly the pictures of what the different norms look like are going to affect the properties quite a lot. So that's what I'm going to try to show you today is like really visually. I know this was in the video. They kind of went over it pretty quickly. Why is it that the lasso does variable selection when the ridge regression does not? And it has everything to do with the shape of this ball. So these are called balls. The set of points where the norm equals some fixed value is called a ball. And the ball in the L2 norm is the ordinary circle. So the ball in the L1 norm is this diamond. And the difference between the diamond and the circle is going to lead to this thing. By the way, a fun thing you can do is you can calculate pi in any norm. So pi is defined as the circumference of the ball to the radius of the ball. So for a circle, it's just pi. It's like 3.14. But for the L1 norm, pi is something like square root of 2, because it's something like that. And for the infinity norm, that's when p is like a bajillion. Let's make p 100 again. Then pi is exactly 4. So what is it exactly? Is it 2 square root of 2? It must be 2 square root of 2 for this guy. For the blue one, it's 2 square root of 2. For this one, it's like 3 of it, and for that one, it's 4. So there's like a screwy proof online where they prove that pi equals 4, and they're actually proving that pi equals 4 in the infinity norm. Okay, so that's what we're going to see. And to understand where this happens, we're going to go back to what we were doing last class, which is looking at these loss surfaces. So I'll remind you from last class, we plotted as a function of beta 1 and beta 2, we plotted exactly this thing, the mean squared error of beta, and then we started adding on terms like this. And when you add on terms like that, this is what it looks like with almost no regularization term. And as you add on more regularization term, it kind of shrinks towards 0 and gets more and more round. So this is what we were doing last time. And this time, I want you to visualize. We were talking a lot about the shape last time, but this time we're mostly going to talk about what is the lowest possible point, the center. Okay. And I think I have a mathematized question for this. Okay, yeah. So I have to show you one more thing. Are you guys with me so far? Any questions or comments? So it's going to start to get even more crazy. So it's a good time for questions. Yeah.
One question. I mean, from the video. When they said summation of beta.
Yeah.
They mean alpha multiplied by beta.
Yeah.
Am I right?
Yeah.
Okay.
So alpha. It's a little confusing because we're using Greek letters for two different things. So alpha is a scalar. It's just some number. that tells you how big should this thing be, how big you want this term to be. And beta is a vector. So if you want to turn it into a number, you have to do something like take the norm. That's exactly what we're doing. Yeah, and we're going to do it for two-dimensional vectors, but you should always keep in mind that it really generalizes to any number where you add up over all the components. Yeah, great question. Anybody else? Okay, so back to this. So that's what we were doing last time. And last time I was plotting for every value of alpha, I was plotting the whole surface, this whole function as a function of beta. And of course, doing the regression means finding the minimum, finding that where it is the bottom of the bowl. And it's always an elliptical shape. It's always a conic section because these things always have squares in them. All right, and now we're gonna try to do a kind of a shift in view using something called the Lagrange multiplier theorem. But instead of just throwing the Lagrange multiplier theorem at you, I want to show you really, it's not a complicated idea. It's quite simple. You just have to work through it a little bit. So what I did is I made this kind of plot, which we also saw last class. And this is a plot of the coefficients as a function of the regularization parameter, right? And we saw this last class. So as you change the value of alpha, the solution you find, the minimum value, so the best possible beta you find, the bottom of that bowl, you have two values, beta 1 and beta 2, and they change as you change the regularization parameter. So what's happening in this particular problem, beta 1 starts at about 2, and it goes all the way down to 0. Beta 3 starts at 3, it goes up just a tiny bit, and then it comes all the way down. And this isn't surprising because the true value is 2, 3. So sort of the fact that they start near 2, 3 is about right. And they go to 0 because as you add on more and more alpha, the optimal solution goes to 0. So that's one way to represent it, and that's the way we saw last class. But I want to represent it in a way that matches this kind of picture. So in this picture, beta 1 is on the x-axis and beta 2 is on the y-axis. And I want to have this idea, like a movie sort of adding more regularization on. So like kind of playing this frame, then this frame, then this frame, all in a row and seeing what happens to the centers. So I made a plot that looks like that. And you guys can tell me what you think if it looks any good. So this is what the plot looks like. This is beta 1 on the x-axis, beta 2 on the y-axis, and I have a color bar here telling me the value of the regularization parameter alpha. Okay? And when alpha is very small, you start near 2, 3. And then as you increase alpha, they go down to 0. And if you make alpha extremely big, so here it's plotted on a log scale, so it starts at 0.1 and it ends at 10,000. If you make it close to 10,000, then of course the parameters are close to 0. And this is just another way of representing this plot, right? So this plot had two coefficients. How are they changing as a function of the regularization parameter? And here I've plotted the two coefficients on their own axes with how far the regularization parameter is colored like that. And it's nice. It looks like a little rainbow caterpillar or something, right? That goes like this. And the one thing we know for sure is it's going to start sort of near what it is for ordinary least squares, and it's going to end sort of at 0. We know that it ends at 0. So this is the picture that we're going to focus on, and this picture is going to lead us to the Lagrange multiplier thing. Any questions about this or what the setup is? Okay, so here is the question this is the important question to ask about this guy. So we're going to think of the optimal beta for this guy. We're going to call that beta hat of alpha, right? So this is by definition, beta hat of alpha is this guy. So colon equals means, by definition, beta hat of alpha is this. And it depends on alpha because when you change alpha, you get a different answer every time. But beta hat is already doing the minimum overall beta. So beta hat of alpha is exactly that curve that I showed you a second ago. This curve, right? So at alpha equals 0, it's here. At alpha equals 10,000, it's here. And it's kind of going through all of those things. It's a curve in R2. So a nice curve, beta 1, beta 2 in the plane. So here's the question. Given a circle of radius c, beta 1 squared plus beta 2 squared equals c squared, how many times is it possible for the curve beta hat to intersect the circle? That's what we want to understand. And there's a few different answers. You can take a look at the picture for some inspiration. But remember, this picture is like one example. I want to know in general, right? If I set it up with different numbers, what is it possible for this curve to do? And thinking about that is going to lead us to this shift in perspective that was displayed in that video to figure out what's going on. So take a second and think, what is going on in this equation that has to do with this kind of intersection thing, and what is happening. So let me start this exercise for you guys to think about. I'll put it in presentation mode, and this will help us figure out what's going on. Okay, so maybe I'll give one more minute. I'll stop when it gets to 3 minutes, and we'll see.
Could you
Yeah.
show the shape?
I can show the shape
Yeah,
again.
Thank you.
Yeah. This one.
Yeah, thank you.
So I tried to recreate the colors on the board. I used less colors than on the computer. Okay, so 5 more seconds, and then we'll see what you guys think. So it was a select all, so there's more than one possible answer. 4 people said 0 are possible, 4 people said 1 are possible, 6 people said 2 are possible, and 3 people said 3 or more are possible. So I want to talk about 0 are possible. This is definitely true. And you can just see that in the example that we did. So this is the nice thing about having an example where something happens. 0 are possible is definitely true. When will you have 0 intersections? There's actually a really nice way to see. There's like a really simple statement. You have 0 intersections when something about the radius c.
When C is too big.
Yeah, when c is too big. And what does too big mean? So c is too big. No intersections. And there's a really precise way you can make this precise. What does too big mean in this situation? How do we know if it's too big or not?
Maybe bigger than the 2 norm of x1, x2.
Yeah, exactly. So it's whatever this starting point, right? This is what happens for ordinary least squares. Beta hat. If you make the parameters 0, alpha equals 0, then you have the ordinary least squared solution. And as you make alpha bigger, if you make it positive, you're always moving towards the origin, right? You can never get a bigger solution than the one you started with. So c is too big. This means precisely c is bigger than the norm of beta. I'll call it beta ordinary least squares. The 2 norm. So sort of, there's this big circle, like this of where you start, and you're always shrinking towards 0. So all the circles that are bigger than that, they don't play any role in escape, right? The only circles that maybe matter are smaller ones. And that makes sense because you're making a curve that shrinks, starts at alpha equals 0 here, alpha equals 0 is here. And it's always shrinking. We know from the equation that it's always shrinking, and towards alpha equals infinity, it reaches sort of 0, and it gets like very, very close to 0.
Firstly,
Yeah.
so the circle still passes through a point, at least.
Yeah, so the circle of this radius passes through alpha equals 0 exactly, and then as soon as you make alpha slightly bigger than 0, it's going to be inside a little bit. So for sure, it's possible to have no intersections, and in fact, you have no intersections precisely for these ones. Does that make sense? So your question was, is it possible to have no intersections?
Yeah, so when you drew the circle,
Yeah.
the circle has to pass through at least 1 point on that curve.
So so far I've only talked about big circles. So C is too big. Are you asking me about C is smaller?
No, C is too big. What does
Yeah.
that mean?
So C is too big means it's bigger than the alpha equals 0 radius. Maybe I'll draw it in blue, right?
But
So
C depends on beta 1 and beta 2, right?
it depends on whatever the estimator is with alpha equals 0.
Okay.
So alpha equals 0 is this point. This is the starting point, alpha equals 0, which is ordinarily squares. And you can never ever have C bigger than the norm at that point. So this is at alpha equals 0. And that's because you're always shrinking in. So here, at this value, you'll have exactly 1 intersection of the alpha equals 0, and anything bigger than that, you'll have no intersections. So it's good. It's good to clarify and to see like geometrically what's going on, right? Okay. Okay. So that's that. Let's look at the other answers. So 4 people said 1 intersection is possible. And I think, again, if you just look at our example does often have 1 intersection. So if you draw a circle of a different radius, let's pick a different color here. So if you draw a circle like that, of smaller radius, in the example we did, it seems to have 1 intersection. So I think 1 is possible, just from the example we did. The question is, could we have run the example if we changed the numbers in the example? Could the curve do something like this? It starts here, it goes for a bit, and then it comes back, and then it goes like that. Like, is this possible? That's the question. Could this happen? Because this one would have 2 intersections. If you do something like that, or I guess 3. So, is this possible? Oh, I guess this also, I hadn't even thought about, there's something interesting that happens about 2 versus 3 being different. So I'll let you guys think about it and vote again. So you gotta ask yourself, could it do something like this? Or based on the equation, is there something about the geometry that is stopping it from doing this? Okay, so I'll give you guys another minute to think. And yeah, there's like a funny thing going on here that I didn't even think about when I made the question. So let's run it one more time. Or, does it let you change your answer if I just hit play? Probably not, right?
I have a question.
Yeah.
So the circle, where will the circle start? Does this have to start from the origin? Or
It's always at the origin because we're always looking at the norm of beta. So the circle represents the equation from the warm-up question. It represents the equation beta 1 squared plus beta 2 squared equals some constant.
So I was thinking like you can fit the circle anywhere on the graph. Then maybe you can fit at a corner. Then
Yeah. So if you want to put a circle over here, this is a great point. So suppose somebody's like, I'm interested in circles around this point, right? That would be the equation. That is not the equation. What's the equation of this circle? So the equation of the circle around the origin is the norm of beta squared equals c squared. That's the circle. That was in the normal question. The equation of this circle over here is not this. It's not norm of beta squared equals c squared. It's something like this. The norm of beta minus center squared equals c squared. So it has a different equation. And you could do this, everything we're doing, you could do it with this, and all you would have to do is change your regularization. Instead of trying to make the norm of beta squared, you would do the norm of beta minus the center, where you tell me what the center you want is, and you square it. And that would be like, I really want my coefficients to be close to the center value for some reason. But of course, in real life, we like the coefficients to be close to 0, because that sort of makes the model simpler, and that helps us with like variable selection and stuff. But maybe you have some special reason to do this. Actually, I'll tell you, in neural networks, you sometimes choose the center to be where you initialized the parameters. So in neural networks, the parameters, you start them out randomly and then you move them around. And for some reason, maybe you don't want them to move very much. So you see like, I want the neural network to just chill out and like take a break. Like don't move around so much. So I'm going to put in a term that says stay close to where you started. And then you exactly end up with that. So that's a great question. We're sort of, by default, we have the 0 because we're just doing normal beta squared. And beta is like beta minus 0. Okay. So let me run this one again. And you guys can take a stab at 2 versus 3. So I gave you I gave you the hint that 0 and 1 are both possible. You got to tell me about 2 or 3. Do you think it's possible or not? And again, so I'm trying to get your brains into thinking about this geometry so you can understand what's going on. Yeah.
I still don't quite get why it is the norm of beta, original beta, that least square beta is the boundary. Would it be possible that it go out a little bit first?
So yeah, so the reason it can't go out a little bit first is if it goes out a little bit first, that means that the norm of beta squared, this term, is larger than when it started.
Yes.
And you told me to minimize it, and you added on a penalty term. So if you minimize it and you add on a penalty term and you get a solution that is even bigger than the one you started with, you must have screwed up your minimization. Because it would have been better to just give me the solution at alpha equals 0, right? That would have...
I just wonder if it's possible that for the first part, the MSD part get lower, and then somehow allow the beta to go higher.
Yeah, you're exactly thinking of it exactly correctly. So the reason the MSE part can't go any lower is because if alpha equals 0, we're finding the beta that makes the MSE as small as possible, right?
Okay.
So when alpha equals 0, we're just minimize just the MSE.
Yes.
So this point, alpha equals 0, is the point in the entire plane that has the lowest possible MSE. Because the MSE is like this big bowl, and this is really the minimum of the bowl. Right? And so as we increase this term, we're saying you can go up the bowl a bit, you can make the MSE larger at the cost of making this smaller, right? And then it's that trade-off that leads us down to 0. But you can never like there's nowhere in the plane that has a better MSE than this point. So if you take somewhere over here, it has a worse MSE and it has a worse norm, so of course it's going to be a worse solution. Does that make sense?
Yes,
and if you take on the other side, it has a worse MSE still, but it has a better...
Exactly, yeah, that's exactly right. So really, I think that's really the perfect way to think about it. And this is why I'm giving you guys the time to digest the problem a little bit. So there's these two terms, and the MSE is absolutely the lowest here. It's like a big bowl around here. And so if you go further out, you make the MSE worse, and you make this term worse, so you're making it worse both ways. If you go in a bit, you certainly make the MSE worse, but you make this one a little bit better. And this exactly what this curve is saying is that the optimal value, depending on what alpha is some curve like this. And if you make alpha big enough, it'll eventually go to 0. That's another fact, right? Okay, this is very good. Okay, so let's see what you guys think. I think this is we're starting to get to the answers. Here. All right. So everybody, 5 out of 6 people, 6 out of 7 people. No, 6 out of 7 out of 8. But it's like I'm like an auction here. Okay. 0 and 1 are possible, like we saw. 2 and 3, it turns out, are impossible. So most people have the right idea. So for one thing, and I didn't even know this when I made up the question, but 2 is impossible just on the grounds of topology. Like there's the outside of the circle and the inside of the circle. And if you had, you start on the outside of the circle, you end on the inside of the circle, so you can't cross it just twice. If you cross it twice, you would go inside and then outside, you'd be outside. So you have to do it for sure an odd number of times. You cannot just cross an even number of times. So like this one has 3, but 2 would be impossible just based on counting insides and outsides. So if you cross once, you're inside. If you cross once, again, you're outside. You could cross 3 times, maybe, but it turns out 3 is impossible. And this kind of situation of ever getting bigger, you can never, on this curve, the radius is always strictly decreasing. It can never increase. So on this little segment of the curve, we saw this kind of segment is impossible where the radius is increasing. And that is exactly for the discussion we were just having a second ago. So I'll say it a little more formally, but let me say it really like intuitively now. Your MSE term and your norm term, so if at this point you've increased the radius, this term is getting worse. So you should have, at this point, there's some kind of mistake either in the optimization here or here, because here you have a bigger alpha, but a bigger norm as well, and you're telling me it's optimal. Like it's impossible. So that's like very roughly speaking, this kind of going up is impossible. And I'm going to make an even more precise statement that I think will make it really clear. Yeah?
Sorry. 3 is, from what I understand, 3 is impossible.
That's right.
It's easy to understand. But about 2, I was wondering, when we cross alpha equals 0, under the point you marked, if the slope of this curve is like this, I mean the circle may touch it twice.
So it's going to turn out that I can only touch it once, but I see you're saying it could be like tangent or something, and like something.
Yeah, if it is like this.
So I think it probably could be tangent at the point, but for the reason we're about to see, if it is tangent at the point, it's going to immediately like go off. Mm-hmm. So in the same way that the function like y equals x squared, right? That looks like this. So that function's derivative is 0 at 0. It's sort of flat. It touches the x-axis, but it only touches it at exactly 1 point, even though it's flat there. So I think that could happen. But I don't think it could be something like, you can't do like this or something. This is like y equals x squared minus 1. Right? It can't do that. That's what we're saying. Okay. So here's the precise statement. Maybe I'll leave that one up, and maybe I leave this equation up too because it's important.
I'm sorry, I do have one more question.
Yeah.
Is the MSE always convex?
The MSE, it turns out, is always a square function. So it's not only is it always convex, it's always some kind of high-dimensional elliptical surface like we saw. So it's always a bowl. Okay. In 2 dimensions, you can think about it really like a bowl of cereal. In 10 dimensions, you got to think about it like you're a 10-dimensional alien who has a bowl of cereal that's 10-dimensional. But it's always that shape. And it really is because, just look at the equation for the MSE, it's all the data points you see and it involves squares, right? That's the formula for the MSE.
No matter what data set it is.
So this is given the data set, right? So this is a function of the x's and the y's we were given. You compute the MSE, and that depends on beta, right? The coefficients beta, and different values of beta have different MSEs. We want to find the best. But this is a good point. And in more complicated problems, this will start to be non-convex, right? So this is a nice square function because this is like linear regression. If you're doing neural networks or something, this becomes some crazy complicated thing. It's still good to think about. Yeah, great question. So here's the statement. The statement is that beta hat of alpha, if the norm equals c, then beta hat of alpha is the minimum MSE on the circle. So what it's saying is, anytime you draw a circle like this, and you look at if it intersects, the point of intersection is the minimum possible MSE of all the points on the orange circle. That's what the statement is. And if you believe this result, so if the norm is C, then it's the minimum. Then of course there can't be like 3 intersections, because that would be like 3 minimum points, right? So because there's only one minimum, if there's only one minimum of the function, the mean squared error function on this circle, then that blue point, the intersection point, is that minimum point. So it can only intersect at most once. There can't be 3 intersections, because there's only one minimum for the function. And this is actually really easy to see. Like, this is not some kind of like crazy magical result. The reason is because you have this term, and on the circle of radius c, this term is just a constant, right? So in general, this term is changing as you change beta. But if you only look at points on the orange circle, then that term is always c. So what you're doing, minimizing everything on the circle of radius c, is the same as minimizing the mean squared error. So let me write that out a little more formally. So if someone says, do the minimum of beta of the mean squared error on the circle of radius c, such that the norm of beta squared equals c, that's the same thing as doing the minimum of the mean squared error plus this extra term, because the extra term just doesn't do anything. The minimum of beta anywhere, beta plus alpha times the norm of beta squared, and then I'll do a minus alpha c squared, so those cancel on the circle. And this is equal to the minimum on the circle, so we'll call this the minimum on the circle plus a constant. So I don't know what to say. Yeah, this is beta, but this is beta hat at all. Oh, okay, yeah.
Sorry.
Yeah, it's yeah. There's a distinction between minimum and arg minimum. So when you add on a constant, it doesn't change where the minimum is. I guess this whole time I've been saying minimum. I actually mean the arg minimum. I mean the location of the minimum. So let me just add that in. Okay, so I didn't do this in like super detail. I think the details are going to confuse the very simple idea that on the circle, the second term is constant. So if you're maximizing over the circle, or rather minimizing over the circle, you just end up with the point where the mean squared error is the minimum. Okay, so this simple thing shows you that you can intersect each circle at most once. And in fact, because you start over here and you end at 0, you have to intersect at least once, right? You start on the outside and on the inside. So this curve goes through all the possible circles that start over there and then here. And it really just has to do with the fact that we used the norm in our equation. Was there a question that I missed?
No, that was
Okay.
exactly what.
Okay, yeah. So it's the English use of minimum is not the same as the math use of minimum sometimes. Okay, why is this important? Why is this important? What we have discovered is a version of the Lagrange multiplier theorem. So in the video they just said by Lagrange multipliers, you can do this thing. But we've just discovered a very simple explanation why. It doesn't involve any magic, so you don't need to be a French mathematician to know. And so what we've discovered is that this curve, beta hat of alpha, which does this minimization, it's the exact same thing as the following curve. So this curve, beta hat of alpha, that starts at the ordinary least squares solution and goes down to 0. This is exactly the same as minimize on the circle. So you could do beta hat of c, which is equal to the minimum of the mean squared error as a function of beta. But not the minimum everywhere, only on the circle of radius c. So only on norm of beta squared equals c squared. And what we've discovered is that the curve beta hat of alpha, which is in alpha space, as you change this parameter, that goes from starting here and ending here, is exactly the same curve as beta hat of c. Start at this radius that you originally started at and end at 0. So the curves, maybe I should say it, the curves beta hat as alpha, and so alpha is between 0 and infinity, and beta hat of c, I'm going to write c is between 0 and whatever you started at, the ordinary least squares So as you change the alpha parameter from 0 to infinity, you do this curve starting here and ending here. As you change the radius from 0 to the original thing, that's going to be exactly the same curve. And why is this useful? Because this new way of thinking about the error really involves the geometry of the norm. In everything I've done so far, I've never ever used the fact that this circle is actually a circle. I've only said it's the place where the norm equals a constant. So everything I've said works for all the norms that we had in norm 1. So it works for the circular norm. If you change to the 1 norm, that'll exactly be the lasso. And that explains why, in the video, they were doing things where they were drawing a little diamond here and talking about where on the circle is the norm minimum. So that's what we're going to do next. So I just wanted to show you guys this really simple idea. It's not magic. It's not like saying it's by the Lagrange multiplier theorem is true, but you really don't need, you just need to think about it a little bit to see. So this is like a new way to parameterize the curves, not by the alpha value, but by the radius. And in fact, in the videos, they often did that. They took the radius, they made the c, and they said c divided by the norm of beta is between 0 and 1. So they had these plots that went between 0 and 1. That's exactly what they were doing. They were saying, instead of going by alpha, go by the c value, and make it so that the original value was 1. So start at 0 and go to 1. Okay. All right, so all of this time, all I've been just getting the simple idea that when you do ridge regression or any other type of regularization, what you are doing is looking on different values of radius, and you're trying to minimize on that circle. And you just get a reparameterization of the curve with the alpha value. So that's a simple idea. In a second, we're going to see why this means the lasso is different than the ridge regression, but this is a good time for questions. So in the video, they just said this in like 1 second. They said, by the way, this is the same as that, keep going, right? So I wanted to show you guys why it's true. It's not a complicated thing. Okay. So now we're going to look at this for lasso, right? So for ridge regression, it's a circle. And okay, it's a circle. And what you have to do is, again, I think there's another good reason to know this picture that we did last class, which is that the lost surface originally looks like this, right? So when you do ridge regression, you draw sort of a circle around the origin, and you find where on these contour surfaces on the circle is the minimum. And the same thing works for the lasso. So everything I've said here works for any norm, and in particular, it works for the lasso. So what we're going to do next, we are going to do minimizing the lasso, minimizing the mean squared error on the diamond. This is for ridge regression. This picture. And then for lasso, instead of having an orange circle, you have a diamond. It looks like this. So this is the set where the 1 norm of beta equals constant equals c. And we're minimizing the mean squared error. So what does the mean squared error look like? I'm going to try to copy this picture from the graph. So it's some kind of bowl shape like this, where the true minimum is here. That's the minimum. And then it has these contours, right, that are getting like that. So and here maybe the value, so here's the minimum value, maybe let's say that's 10, and then here it's 20, and here it's 30, and 40, and 50, and so on. So is it clear what I'm plotting? So I'm trying to plot a 3-dimensional function on a 2-dimensional board, so I'm drawing the lines where it's always a constant. You can kind of see the bowl shape. You have to visualize it coming out of the board, right? And so for the lasso, you see, for a given value of constant c, you see where on this square is the minimum. And that means like, which line do we reach? What's the closest line to the maximizing value that we reach? And in this case, I think it's this line 40. So it's this point right here. At this little diamond point, that you touch the line 40, all the other places on the square have a bigger value. So for example, down here on this line, you have 50. Between here and here, you have something between 40 and 50. Here you have something between 40 and 50. The minimum value is this diamond point. And here is the big difference between the circle and the diamond, is that the diamond has these pointy corners. And the corners, if you draw them correctly, should be exactly axis aligned. So they should go through exactly these points. And when you have a minimum happening at a corner, that's exactly corresponding to the value being where one of the coordinates or more of the coordinates is 0. So at this point, this is the point, beta 1 equals 0, beta 2 equals something. Okay. So when you do the lasso, you're maximizing over the diamond, and the diamond has points. Very often, the points of the diamond are the places where the maximum happens. I keep saying maximum, but I mean minimum. So it's whatever, it's a minus sign, just say. And that is why the lasso will do this automatic variable selection. It'll choose things to be 0. This kind of thing would not happen with a circle, right? So when you draw the same shapes over here, there's no points, and you just end up with some kind of point that's tangent to the circle, not necessarily directly in the direction, right? That's why the curve is not just a line, but it's very rarely one of the two coordinates. So that's why the diamond is different than the circle, and that's why the lasso, with its 1 norm, is different than the ridge with its 2 norm. Question over here.
Yeah, sorry. In the video, I was wondering why the loss function exactly cross the point at the edge of the diamond.
Yeah. Why does it cross the point? So I just did an example. I just drew it on the board, and it just happened that it was on here, right? So it'd be good to know. Does it always happen? And the answer is, of course, no. Like you can imagine, if I move this point, now let's do another example. It looks like this. So here's the diamond. Let's try to make an example where the minimum is going to happen somewhere on the edge, right? Why don't we just put it like here? Let's do it like this.
Yeah.
So then, if the true point is very close to the edge, then the minimum is just going to be like somewhere here. Okay. So it's like a really good question that like one should ask. If you were like a really good teacher, you would prepare this as a question. When is it on the edge and when is it on the corner? So let's go to the computer, and the next mathematized question is, when is it on the corner and when is it on the edge? Okay. Where is it? All right, okay. Okay, so here's the setup, and it's a little bit of a long one, so let me walk you through it. But it is just what we did just on the board. That's not the question. I want this question. I want to present it. Okay. So consider optimizing a purely circular mean squared error loss on the surface. So in this example, I drew them with ellipses. In this example, it's always going to be a circle. So you should picture, for this question that we're going to do on magnetize, the mean squared error is always a circle, which of course is, it's some kind of special case, but they're circles.
So the circle means we standardize the parameters?
No. So standardizing normally is what you do to the data, right? And but we're working in beta 1, beta 2 space. So it's just like, it just means there's some kind of coincidence, some cosmic coincidence that happened where the beta 1 direction and the beta 2 direction happen to be like the same. And it really is just a simplifying assumption. If you can understand how it works with a circle, you for sure can understand how it works with a diamond or with any ellipse. So it just means that the bowl coming out of the board is perfectly symmetrical. It doesn't have a special direction, it just has circles. That's what it means. Okay, you apply the lasso, so you're doing this diamond thing, beta 1 plus beta 2 equals 1. And it naturally divides the plane into 8 regions, which are labeled according to clock notation. So here is the picture. Here's the diamond, and here are the 8 regions of the plane. So here's the diamond, and then there's sort of 12 o'clock, which is directly above it. There's 6 o'clock, which is directly below it. There's 3 and 6, or 3 and 9, to the left and to the right. And then there's these like square regions, 1:30, 4:30, 7:30, and 10:30. And they're all sort of like, they have special properties sort of with respect to this diamond, like where they live. And in some of these regions, you end up on a corner, and in some of them, you end up on the side. And I want you to decide which one is which. And to help you guys, I made a Desmos. So if you copy paste the link from Desmos, and you can also find it on the course GitHub, if that's easier, you end up at this Desmos. So what we have is exactly like this. So here's the diamond. Here's the diamond. And here are the 8 regions, 12, 3, 6, 9, as well as 1:30, 4:30, 7:30, and 10:30. And what I'm asking you here's our circular thing, right? And where do you put, depending on where you put it, you will either end up at a corner or you will end up on a line. And the question is, if it's in this region, what happens? If it's in this region, what happens? If it's in this region, what happens? If it's here, what happens? And you have to tell me, do you end up on a corner or do you end up on the edge? And I'm telling you, I guess I'm giving the spoiler, but the answer is the same for all the points in one region. So if you start anywhere in this region, you should get the same answer. If you start anywhere in this region, you should get the same answer. So some of the regions end up at corners, some of them end up on the lines, and you can explore it with the Desmos thing. So you can make this radius bigger or smaller in Desmos, and you can see what happens. And I'm going to give you guys a minute to play with it or like visualize it or draw mathematically. So if I tell you the answer, I think maybe you won't appreciate as much what's going on. But this will exactly answer the question, when do you end up with a zero variable and when do you not? Okay, so let me open it up. So choose the ones where the lasso eliminates a variable. Where does the lasso eliminate a variable? Which regions? And those are your choices, and those are the regions. Select all the regions that you think. Okay, so I'll give you a couple minutes to play with that. And yeah, I think that if Mathematize doesn't let you use the link, probably the easiest way is to go to the course GitHub, and then you click on Desmos links. And today's November 8th, playing with 2D regions in the lasso. That link should take you to the right spot. Let's see if it's working. Okay, yeah. Yeah, and this is draggable, so you can drag around the center, right? That's what I'm asking you when it's in one region versus the other region. And you can also play with the radius, right? These are just contour lines. You can draw a contour line at any radius you want.
So the dots on the right is that a minimum or
You mean like the little bullseye?
Yeah.
So that the dot is the bottom of the bowl.
Okay.
And then the rings are the like different contour lines, just like I had 10, 20, 30, 40 before.
Okay.
So the center of this is the absolute minimum of the mean squared error. And the circles around that are regions that have a slightly higher mean squared error than the actual minimum. Right? So it's kind of a representation, just like the loss function we did last time. This one was an ellipse. That one is just a circle. That's the difference. Yeah. And of course, in a real problem, you don't like choose where this is, right? Like here, we're moving it around. In a real problem, this is given to you. It's one thing, and you're minimizing, right? But for this problem, we're saying where in the region would it have to be for a certain thing to happen. So that's why we're pretending we're moving it around. Okay. Okay, so I have 6 answers. Maybe I'll go 1 more minute. It's okay, take a guess. And we'll see what you have. So I'll stop when it says 7 minutes. I will stop. And again, yeah, there are 8 regions, but if you see the pattern, it's actually not so complicated. Okay, so 7 minutes. Let's see what you guys said. All right, so it looks pretty split. So, 2 to 6. Okay, so, all right, actually, this is quite good. So, out of 8 people, 6 people, 7 people are on 12, 3, 6, and 9, whereas 2 people are on the 30s. So, looks like most people are saying the regions 12, 3, 6, and 9, the regions to the sides, and only 2 people are saying these like rectangular regions. So let's see. Let me show you how you would find the answer in Desmos, which is probably how you did it. So let's do 12 o'clock first. So you're somewhere in this region, and let's pretend you're there. And really, what the question is, right? We want to find, as you increase the radius here, you're making the mean squared error worse and worse. You want to find out what is the minimum possible amount to add so that you touch the purple diamond. So I'm just going to increase this as much as possible until I touch the purple. Okay, here we go. I'm increasing, I'm increasing, I'm increasing, I'm increasing, I'm increasing. Stop! Okay, so here I just barely touched it. And so that means when the true value is here and you have circular regions, the lasso value on this diamond will be right here on the corner, just like we did over here. And actually, the same thing is true anywhere in the region. So if you go over here or something, you have to increase the value more, but always the very first place you stop is touching that corner. So anywhere in this region, the first place is the corner. So 12 o'clock is the correct answer because in this region, you end up at the corner, and the corner has an x-coordinate of 0. So beta 1 equals 0. So the lasso, if the true value is anywhere in this big region up here, this 12 o'clock region, it will eliminate a variable. What happens if you're in the 130 region over here? So let's start over. So here you increase, 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 stop. And you stop here. And here you're touching on the side. And that's going to be true anywhere in this region, right? So anywhere in this region, you will stop on the side. Sometimes you'll be close to one of the corners, but you'll always be there. And the same pattern works everywhere. So 12, 3, 6, and 9 are all the regions where you eliminate a variable. And if you zoom out enough, you can see that those regions, 12, 3, 6, and 9, cover almost the entire plane. What is not covered are these like little rectangular strips. So depending on how big you actually made the lasso parameter, like depending on how zoomed in you are, because remember this diamond, we're changing the size of it, most of the region sort of has this property. And of course, this is purely kind of theoretical because this is 2-dimensional. In real life, we have 1 dimension per parameter, so it could be like 100-dimensional, and then you have some kind of hyper diamond. And these directions are never perfectly circular, but this illustrates what's going on. So this circle is always some kind of ellipse, and this diamond is always some kind of hyper diamond in many dimensions. And this is like why the lasso is eliminating variables. So hopefully that helps you see what's going on a little more clearly than they did in that 2-minute segment on the video. Any questions or comments for this one? I think most of you guys got it right. So either you understand or you're good at answering questions. Okay, so in the last couple minutes, a couple small things. One thing is, remember, we said you could do any of these. So what if we did p equals 0.5? We made it even more pointy, right? Then we would have even more regions where we eliminate, right? So why don't we do this thing with p equals 0.5, then we replace the diamond with this super pointy guy, then we would have even more variable elimination. What do you guys think? Or should we write a paper? Propose this new method. So it turns out there's a problem with this. And the problem has to do with the following question. I'll ask quickly in Mathematize, so this will be a super quick one. It's like a true or false. So last class we found a nice formula for the ridge regression in terms of x and y. Is it possible to find an equation like this for the lasso estimate? So last class we had this equation. It was x transpose x plus beta times the identity matrix inverse times x transpose y. And we derived this last class. And it's a really nice formula because it just involves linear algebra and inverses, and we talked about how adding beta actually makes the inverse better. Could you do something similar for the lasso? So yeah, give me your best guess, yes or no? Okay, let me see what the yeses or nos are from the first few people. If you want to put in a guess, go for it. So the answers are no, yes, it's split. So it turns out the true answer is no, you can't do it. And that is because this operation of doing the 1 norm does not play nicely with the matrix operations. So the 2 norm was really nice because the 2 norm came from matrix multiplication. It came from Pythagoras. It's got everything to do with everything. And it really has this property, the 2 norm, the L2 norm, goes with inner products or dot products. And because the 2 norm goes with dot products, you can come up with nice formulas like this from Pythagoras. The 1 norm is a norm, but it does not come from any inner product. So you can never get a nice equation like this for the 1 norm. So when you go to solve for the lasso, you can never have a nice formula like this. What you have to do is you have to do something called convex optimization. So here's some Wikipedia page about convex optimization. So this is what some people study, and these are the version of the Lagrange multipliers theorem for convex optimization are called the KKT conditions. And so there's some kind of like computer program you can write to find the minimum without getting a nice formula for it. And there's like a whole field of analysis that has to do with convex optimization. And hopefully this triggers you on what is wrong with the green star that will not work. So the blue region, even though it does not have an inner product, it is a convex set. And when you're minimizing over a convex set, you have all this theory from convex optimization. So the reason nobody can make a version of the lasso with the green pointy star, it would be nice, but there's no way for your computer to find the actual maximum. Because it's not a convex set, you don't know how to tell the computer, please find the maximum. In 2 dimensions, you could just check every single point. But in 100 dimensions, that's not feasible. You need some kind of smart way to find the minimum. So in summary, the red region, ordinary bridge regression, is super nice. You just use linear algebra. The blue region is the lasso. You use convex optimization. You cannot do it with the green one. It's just impossible. Even though you would get very good, you would get very good, what are called sparse estimates, right? A lot of the entries would be 0. Okay, in the last 2 minutes, I won't go over, but I will point your attention to the Jupyter notebook adding in the lasso. So everything we did last time for the hitters, right? Trying to figure out, using ridge regression, how the variables change as a function of the parameter. You can do that again with the lasso. So if you do it with the lasso, you get a nice picture that looks like what? What does it look like? Like this. So as you increase the lasso parameter, you're ending up on those corners, and a lot of the coefficients get set to 0. And so what it looks like is you go, and you hit 0, and then that coefficient is 0 forevermore. And again, just like there was the function ridge CV, there is a function called lasso CV, which is automatically doing cross-validation to find the best value as before. So all of this is exactly the same for the lasso and ridge regression. The advantage of the lasso that you can sometimes use is that the final model you get, so it looks something like this, it'll have a lot of actual zeros in it. So you know, at the end of the day, the only coefficients you're using are like what division you're in, how many home runs you had, stuff like that. You're not using things like how many times you were at bat. So that can be useful if you want, but from the point of view of actually using it in software, it's exactly the same as ridge regression. I also, based on our discussion last time, I redid this notebook with and without normalization. So here it is. Without normalization, it looked like this, and it kind of looked like what division you were in was really important. But it turns out that was only because division was 0, 1 valued. So if you normalize the coefficients beforehand, it looks like this, and then division suddenly does not seem as important. So depending on how you put the things in the data, you get different looking plots. So that might be good for you guys to check out, but you guys can do that on your own time. On Thursday, we're going to start dimension reduction and principal component analysis. Okay, let's stop there.